Hi, I'm Dan Herbert, course developer and tutor at Point Blank Music School. This is the third video in this series in which we're going to look at the FM synth engine within Rounds. We cover complete in our sound design courses and diploma courses here at Point Blank. To find out more information on our courses online in London and LA, head over to pointblanklondon.com and also be sure to check out the other videos in this series. So to begin with, I'm going to initialize all the settings. The quickest way to do this is come to the created for arpeggiator bank, arrow down and find init rounds. And then we want to deactivate all the cells apart from digital 1. So now when I press a key, we can just hear a pure sine wave. So let me just move this window across. And then we can see when I play a note, we've got one harmonic there, and you can see in the oscilloscope view, it's a sine wave. So in terms of the interface for the digital synth, you can see it's divided into 5 sections: pitch, oscillator, filter, modulation and output. And we're mainly going to focus on the oscillator section. FM synthesis can be slightly confusing, so let's take a look at this page from one of our sound design courses in which we cover FM synthesis in more detail. And this diagram helps to show the concepts involved. So we can see here the output of oscillator A, which is known as operator 1 in Rounds, modulates the frequency of another, in this case the carrier, and it's no different to me ramping the frequency control up and down with my mouse. However, when the frequency of the modulator is at an audible frequency, then it starts to create sidebands, which results in more complex tones. So let's play a note, and the sound we're currently hearing is from the carrier only. So you can see down here we have this algorithm, and this represents the 3 oscillators, 2 modulators and 1 carrier. So to start with, I'm going to pull the frequency of modulator 1 right down by setting the ratio to 0 and just offset it there. Now let's increase the modulation amount. And you can hear and also see on the oscilloscope we're creating a vibrato effect. And this is essentially all frequency modulation is. However, when we start to speed it up, then it starts to create these more complex sounds. Every so often, you'll find the sound becomes harmonic, but in between quite dissonant. So we have 2 main parameters which affect the timbre of the sound. Let me just reset that by double clicking, and I'm going to set the ratio back to 1. So the ratio determines the frequency of the modulator in relation to the carrier. So on a setting of 1:1, it means it's at the same pitch, and as I slowly increase the modulation amount, then we create something akin to a filtered sawtooth. If I set the ratio to 2:1, that means the modulator is an octave higher. It's twice the frequency. Now let's increase the modulation amount. We get a bit more of an open sound, very similar to a filtered square wave. As I push it higher, then we start to get these really bright digital textures. So you can see the modulation amount and the ratio work together to affect the timbre of the sound. If the ratio is on a whole number, then we'll get a harmonic sound. Or if we start to adjust this fine control here, we start to get dissonant textures. So let's reset the fine control. And then what we typically might do is make use of an envelope to control the FM amount. So if I come over here to the modulation section, let's click on here till we see FM1 and then push up the envelope amount. And let's just pull down the FM amount so it's not so bright, and then tighten the decay. I'm also going to tighten up the release on the amp envelope. So you can hear, if we turn off the envelope, just a sine wave, but now we've got a nice attack to that bass sound. We can also adjust the ratio again. Okay, what we might do, just adjust the envelope to tighten the sound up. So FM synthesis is different to subtractive as it allows us to add harmonics rather than just filtering an existing waveform. The ratio here can actually be switched to intervals and the difference in pitch set in semitones. So what you'll find is values like 7 create a fairly harmonic sound, or 12, which is an octave, and any other values will typically be quite dissonant. So we actually have 3 oscillators in the oscillator section: operator 1, operator 2, and the carrier. So let's just set up another sound where we use both operators. So this algorithm down here determines how they interact with the carrier. So at the moment, switch to parallel. Let's just reset the mod amount there. And I'm going to set this to 9. Let's play lower down. And I just want to give this a little bit more movement, so I'm going to make use of the LFO. It says FM1. And let's just give this sound a bit more body. And I'm also going to adjust the fine control here as well. Just gives a little bit more movement. And if I want to, I can push this higher. So you can hear the LFO is actually modulating the FM amount here. Now, if we switch this to serial, we'll get a slightly different sound, as now operator 1 modulates the frequency of operator 2, which in turn modulates the carrier frequency. Still get that movement, and as I push up FM1 amount, sound gets brighter and harsher. So you can hear the difference in the sound depending on whether we use the serial or parallel algorithm. We also have here a feedback parameter. So I'm just going to pull down the modulation amount of both these and reset it here. So the feedback control basically routes the output of an oscillator back into its frequency input. And what we typically find is it creates the sound of just having an oscillator of 1:1 ratio. So we're going to create a kind of sawtooth wave. And then beyond this, it starts to generate noise. Okay, and we can actually move this feedback anywhere we want to in the algorithm. So to hear this, we'll need to push up the modulation amount. So now operator 2 is feeding back on itself. Or we can actually feedback operator number 1. I also really like the spread control, which detunes the oscillators against each other and really thickens the textures and creates a richer sound. There's actually 3 modes to choose from, so what I'm going to do is just simplify what we're doing here, take the feedback off, and reset this as well. Now let's push up the spread. So you get this kind of chorusing effect, almost like a Leslie speaker. It's got a nice pulsing to that sound. We can also change the spread mode. So I'm going to pull down the frequency modulation amount there. And then choose spread 1. And you can see now up in the spectrum view how we've got 2 additional harmonics. An octave below and an octave above. And spread 2 where the harmonics are now 2 octaves apart. And create these bigger stacked sounds. The op-out here is quite a novel feature and routes the outputs from operator 1 and 2, so sometimes useful for creating a bigger sound depending on their tuning. So this is used to great effect in the FM House snapshot, for example, which you heard in the intro to this video. So this snapshot is comprised of 2 sounds. For now, let's just solo 2, center the pan, and take off the reverb. And let's pull down the op-out and push it up. So So you really hear how it underpins the sound and fills out as well. This sounds actually quite interesting for a number of different reasons. Obviously the reverb on there, but the two sounds are panned hard left and hard right, and also slightly detuned to create a kind of wider stereo image. And also they make use of the digitize function in filter. So again, if I solo 2, now digitize basically sample rate reduces the sound. And as I push it up, we get this, and you can see from the oscilloscope view up here how the waveforms decide to look block-like. The other significant difference in the filter section is the filter type, and this varies from a low pass through to a notch filter. So if I adjust the, let me just move this across, so if I adjust the cutoff now, you can see it's sweeping through on that spectrum view and notch out those frequencies all the way through to a high pass filter.